So what we want to talk about here are ways to collect data. And with this section, we're going to focus on observational studies versus experiments. And then we'll go into kind of what makes a really good experiment. So when researchers out there in the real world are starting to run experiments, they have to think about a lot of factors that will reduce bias and make sure that it's not influenced by any outside factors. So one of the quickest way to collect data is anecdotal evidence, and this is where you just get kind of one or two results. And with that, there's a lot of bias in this, or like it often is the unusual cases. So this would be the idea of like just one of your friends saying, hey, I took vitamin D and it made me feel smarter. I got smarter and I aced my test. It's awesome that it worked for them, but that's just one case. In order to actually make a claim like vitamin D makes you smarter, you'd have to run all sorts of tests with many more results. So the key to anecdotal evidence is it's just coming from a few results. And with that, that's not a very good way to have data. Another way we can collect data is through observational studies. And this is where researchers just gather data without interacting with the population. And with this, I always think about like the researchers, they don't manipulate the environment. If they're changing the environment, that makes it an experiment. Then they're changing something and looking for an effect. But if they don't do anything, then they're just observing is the key word in this. They're just observing what's already happened or is currently happening. And that's where we get into, is it retrospective or prospective? So if it's retrospective, then the data is collected after the events. So this is kind of like historical data. So looking back at data that's already occurred, then they're observing it, but it's after it all happened. And then prospective is where the data is collected as it's occurring. Collected as it occurs. So with both of these, the researchers aren't changing anything, they're just recording down what's happening naturally, and it's just with this it's already happened. Here it's happening at the time, but again they're just recording it down. If researchers want to change the environment, that's where they run a randomized experiment. So some pieces to this. Randomized means that they randomly assign into two groups. They're going to have these kind of treatment groups and then a control group, which we'll talk about on the next page. And then they kind of measure how do they respond to what they're manipulating. They kind of throw this factor into the experiment and see how things respond. So that's our response variable. So with this, researchers change the environment. Whether, well, there's so many ways to do this, but often what we hear about are like drug studies. So if they're testing to see if some drug works in a specific way, then they would be doing an experiment because they're changing like what's being given to the person. So let's check out this kind of matching piece down here, where we have these four scenarios, and we want to see which is it of these four possibilities. So with this first one, we have a group of disabled women aged 65 and older, tracked for several years, and they noticed that those that had a vitamin B12 deficiency were found to be twice as likely to suffer from depression. So what we have here is that, so they were tracked for several years in 2010, and then looking back, they saw that those that had vitamin B12 deficiency also had depression. So notice they're not manipulating the environment at all. They're just observing, and they're also observing something that's already, that's occurring, that as they collected it, so this is recorded as it occurred. So with this, it's observational because they're not changing anything. And there's nothing about it being a small sample size, so it's not anecdotal, and it's collected as it occurs, so this would be a prospective. I know I hesitated there because in 2010, that was a while ago, but it sounds like they were analyzed it right after they looked at it. So with that, it makes it prospective. If they were talking about then in 2018, they looked at the results, then that would make it retrospective. With Part B, so researchers are investigating taking aspirin regularly, reducing the risk of heart attack. So 400 people were divided into, or 400 men were divided randomly into two groups. So there's this randomly into two groups piece. One group takes the aspirin. That makes this the treatment group. So they were actually given the drug. And then the other group will take a placebo, and this is called the control group. And a placebo is just a fake treatment. Often it's like a sugar pill, so it won't affect anything, but it's this idea that our mind can play games. If we think we're receiving a treatment, our body will actually respond to the treatment. So we want to be careful of this placebo effect. And then at the end, they analyzed what occurred. So these pieces, the researchers provided a treatment, and they had a control group and a treatment group, and they were randomly assigned. All of this leads to a randomized experiment. So this would be number 4. All of these pieces, along with that randomness, is exactly what we want for a randomized experiment. And we need all of these pieces in order to make it nice and controlled so that we're eliminating any sort of bias that's coming through. We get rid of that placebo effect that can happen. In Part C, we have researchers examined health records. So they're looking at old health records of thousands of males and looking for heart attacks and height. So looking at old health records, that makes this historical data. And all they're doing is just kind of reviewing stuff that's already happened and then making conclusions from that information, and that makes it retrospective. And then with our last one, a doctor worked with 2 patients whose depression was cured with vitamin B12 injections. So that's a very small sample size, and that's going to show us that that's anecdotal evidence. It's great that it worked for them, but we need more information. In fact, if we could get to kind of this randomized experiment setup, that's the ideal for kind of testing, does vitamin B12 injections cure depression? But with just 2 patients, we can't make any sort of claims. So, in Part C above, so where they're looking at the old health records, is it correct to conclude that shorter men are at risk of dying from heart attack? So kind of making this link between height and risk of heart attack. And just looking at historical data, just looking at stuff that was already recorded, we can't. No. We can't make that claim because we don't know what other factors were at work. Because I don't know, it's hard to say since I'm not a doctor, but likely it isn't the height causing the heart attack. It's something else that comes through, within the body, something else that forms that make heart attacks more likely. So it's not likely the height itself, being short itself. It's likely that there are lurking or confounding variables. Those are interchangeable. You can call it a lurking variable or a confounding variable, but it's the idea that there could be some other variable causing the heart attacks. So this often happens with observational studies where we can't make claims about cause and effect. If we're just observing data and whether it's already happened or it's currently happening, we can't say this causes that just because we don't know about the other factors, because there's no control in an observational study. You're just recording what's already happened. However, if we look up above and think about where can we infer causation, which causation just means cause and effect, and what happened in Part B with all of that control there and the randomization and the 2 groups and testing the placebo, that is exactly what we need to do in order to talk about cause and effect. So only with a well-designed randomized experiment can we eliminate lurking variables. With all of those factors in there of the randomization and checking the placebo effect, that's eliminating things that could possibly causing biased results. So if we have those pieces, we're getting closer and closer to being able to talk about cause and effect. So let's talk about what makes a well-designed randomized experiment. So what we're going to do is look at this experiment with chia seeds and weight loss. So they describe some pieces here. Let's grab what they tell us. So there's information if you remember chia pets. Those are a big thing. And what they're doing is taking the seeds from that. You can find in a lot of health food stores. And what they want to see is if you consume them, are you more likely to lose weight? Can it be a diet supplement? So we have here is a team of researchers recruited 38 men, and they divided them into two groups. So we have a treatment group and a control group. Treatment group often actually receives the treatment that they want to test out. Control group often gets a fake treatment. And then they also have 38 women, and they randomly placed half of these into two groups, treatment versus control as well. So one group was given 25 grams of chia seeds, so this is describing the treatment, and they were given that twice a day. And then the other was given a placebo, so letting us know that they did use a fake treatment. The subjects volunteered, and that's going to be something important to note there, just because when we have volunteers, that can influence the data a little bit. So after 12 weeks, the scientists found no significant difference between the groups in appetite or weight loss. So basically no significant results. So, with those pieces that they describe up above, let's go over some vocabulary while applying it to this example here. So describe the treatment groups. So this is the group receiving the treatment or factor. And we have two treatment groups. There's 19 men, 19 women. So it's 19 men and 19 women who are given 25 grams of chia seeds twice a day. So that describes our treatment group, who's part of it, and what is the actual treatment. The control group, there are 19 men and 19 women, and they are given a placebo. So, with our control group, so describing how many there are, and then we know they are getting this kind of fake treatment. So, blinding. What we want, ideally, is a double-blind test. If an experiment is single-blind, that just means the participants don't know which group they're in. Meaning they don't know if they're getting the treatment or not. Which is the whole point of the placebo, in that you want them to think they're getting the actual treatment to see if their body responds. So if we use a placebo, it should be at least single-blind, because you don't want to give a placebo and then tell them they're being given a placebo. That kind of undoes the possible placebo effect. But ideally, we want double-blind, which is where the participants and the researchers don't know the groups. And this helps, don't know which groups, this helps eliminate any bias from the researchers so that they don't pay extra attention to the treatment group, because then that can undo the placebo effect. So, in terms of our experiment, They don't talk about whether or not the researchers know the groups or not. Since they're giving a placebo, we know it's at least single blind. They could quickly change it to double blind as well, if just the researchers don't know, but since that wasn't described up above, we know it's at least a single blind experiment. And has the placebo been used? Placebo is being used. So, that's having blindness in a test. Single blind is just the participant doesn't know. Double blind is the participant and the researchers don't know. Something else we should have is random assignment, in that were the groups randomly assigned. And yes, they were, because it describes up above, let's see, 38 men and women, divided them randomly into two groups, and they were randomly placed into two groups. So with that wording there, yes, random assignment was used. The participants were randomly assigned, and you want to use this because you don't want participants choosing which group they're in. Mostly because, well, that will get rid of the single blind. They'll know which group they're going into. And having random assignment kind of creates diversity between the two groups. It'll eliminate any lurking variables coming through. Blocking. Blocking is where we separate the groups by some factor. And it happens before we separate into treatment and control. It's the idea that really they started with 76 people, and then they separated by gender. So for us, yes, blocking was used, and our blocking variable was gender. They separated into two groups of men and women. And this can be helpful so that male and female bodies respond differently to treatments, especially in terms of weight loss. So with that, it can be important to have an even disbursement between the two groups, like knowing that you have those 38 men, knowing how you have those 38 women, and keeping their data separate just because, based on gender, bodies behave differently. So sometimes it can be beneficial. Blocking doesn't have to be used, but for certain types of experiments, it can be good. Our response variable, so what was measured, so they looked at weight loss, so that's our response variable, and the units probably in pounds for over here in the United States. So they were recording some weight loss as they were given the treatment. So with these pieces, this is all fantastic for a well-designed experiment. Key pieces is we need a treatment group and a control group. Ideally, it would be double blind with the placebo. Single blind is good too. Random assignment is important. And blocking doesn't have to be used, but it can be used. But really, these are the pieces we need to have a nice, well-designed experiment so that we can talk about causation, cause and effect. Because if we have these pieces, we're eliminating enough bias to get to that point. So can we generalize the conclusion to the population at large, including causation? So like for us saying chia seeds cause weight loss, or rather from our results that chia seeds don't cause weight loss since they didn't see a significant difference. So we can conclude causation. Something we want to be careful of though is that we did have volunteers. We go back to that little word of warning here that when we only have volunteers, it does influence the data. However, when we run experiments, really they can only ever be volunteers. You can't force people to do things. So with that, we want to be aware of it, but it's not going to destroy our study. So you can conclude causation, meaning we could say, like, chia seeds don't cause weight loss, something like that. That's what the researchers can conclude from this. So this is what makes a well-designed experiment. If we're the researcher and want to influence the environment, we should think about having these factors involved so that we're eliminating those lurking variables. That's it for this video. See you guys in the next one.